Hi, welcome to the Calculus 1 lecture series. And we are in the unit number 2 and talk about the derivatives. This is our lecture number 16. We're going to talk about another applications of the derivative. It's called the related rate. Okay, and so let's go ahead and go to our lecture notes and see what is in the related rates here. Okay, so what is the related rate? Okay, the related rate problem is like if you have 1 or 2, the given rate of the change is and then you are asked to find the rate of change of some other quantities here. Okay, so that's what we call this related rate here. Okay, so it's an application. Okay, so related rate here, let's put it here, related rate. So it's an application. So what is this one application is, you have one or more, okay, rates of the change. Okay, are given. And then you're asked to find the rate of change. To find the rate of change of some others. Of course, this is, it has to be related, right? Quantities here. Okay, so for example, what is this? So for example, if you are blow the air into a balloon, so the radius of this balloon, we assume it's a round, sphere. So the radius of this balloon, every time when you blow the air in that, the radius going to get increased, right? Going to change, right? That's the rate of the radius change. When the radius change, then I know the volume of this balloon going to change, right? So this is what we call it related rate. That means, your volumes, how fast the volume change is depends on the how fast, the radius changes, right? So of course, like for this example, I just give you, I only have one changes here, but in here you can have more than one changes here are given, and then you are looking for the rate of change of the others. So the reason why the others, this is related to what the rate of the change you're given. That's why we call it is a related rate. Like we talk about the volume of the sphere, the change of how fast the volume of the sphere change will be dependent on how fast the radius changes, right? Okay, so in fact, when we try to do the related rates problem, and there are several very common steps, if you follow those steps, probably will be easier for you to do it. So what I'm going to do is here, I'm going to use the example here. Then we're going to follow this example, and then we follow what is this steps telling us, all right? All right, so the step number 1 is here. When I try to give you the problems here, so here we said, draw a picture. Draw a picture of your problems. Of course, is if possible, right? So so if you draw a picture, so it will be, probably will be easier. Okay, let's take a look at the first problems here. Now we go to each step and we take a look at this problem. So the first problem, let's say a ladder is 13 feet tall, is leaning against the side of a building. So they say if the bottom of the ladder slides away from the wall at a rate of 2 feet per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 5 feet from the wall here? Okay, so let's take a look at our first steps here, right? So I say, okay, so here, this is my wall, all right? And so this is the ground, right? So then here you say, okay, this is my ladder. Okay, so this is my ladder. So the ladder is 13 feet long. So here you sit on this wall here, right? Okay, so now this is the first step. It's pretty easy, right? Okay. Now let's take a look at the second one here. The second step here, I say, okay, after you draw that, okay, the second step is here. So you want to, identify and label, you want to do these two things. You want to label all the constant. So those are the fixed quantities, right? So these are the fixed quantity. Those quantities are not going to change with the times, right? And you want to identify the variables here, okay? So those are the variable. They go into, so the rate of the change of those variables, right? So the rate of change of those variables is given, okay? And so we'll see what is this one here. The rate of the change is given or it's not given, right? So not given, you want to find, okay? So if you want to find it, so it depends. So we want to identify that. Okay, so now let's take a look at this one here. Okay, so this is my graph here. So then the second one's here, they said, okay, if you read the problem, they say if the bottom of the ladder slide away, so when the ladder going down, right? So if you imagine that here, if your ladder sliding down, so that means, that you're going to slide this way, and then you're going to sliding down along the walls, right? Okay, so after you see that, so you understand what's that, right? So here, then let's say identify the variables here. So I say, okay, so I will say this is my x variable, and this is my y variables here, okay? So the x variable, this is the distance, right? So this is the distance between the ladder and the wall, right? The distance between the bottom of the ladder and the walls here. So what is the y here? Is the distance, right? So this is the distance, okay, from the ground. From the ground, I need to write better so you can see my handwriting better. So it's from the ground to the top of the ladder, right? Okay, so here I can say the x is the bottom of the ladder. So we're not confused. Okay, now, okay, so this is then we say, oh, there's a rate, right? So here, let's say there's a rate is 2 feet per second here. So this one you say, you read it, is the bottom of the ladder sliding away, right? At a wall at the rate of 2 feet per second. So what is this given ones here? So the given ones here is dx dt, right? The rate of the distance change with the time, this is 2 feet per second. And the problem want us to find is how fast, right, the ladder sliding down. So this what we're looking for is dy dt. So the dy dt, we do not know, right? Because that's what is the problem want us to find here. Okay, so you list everything the problem telling you, okay? So you list everything the problem telling you, and then, okay, so you write it down, what the rate is given. So like, for example, this is the given rate, right? So this is the given rate, and this is the rate, and this is the rate we are looking for here, okay? So that's the step number 2 here. Okay, so the step number 3 here. To me, I think this is probably is the hardest step. Whether you be able to solve the related rate problem or not, the problem step number 3 probably is the hardest one. So what is the step number 3 here? Step number 3 is you want to find an equation. Okay, so this equation that relates. Okay, so this equation that relates the constants you have and the variable, okay, whose rate are given, so whose rates, okay, so are given, okay, and the variable, the rates is not given, okay? So like I said, this probably, if you can find this equation, and then the remaining part is pretty easy. So that's why I said this probably is the hardest step here. So if you go back to here, so you say, okay, those are the problems here. So I do have a constants here, right? So which one is my constants here? This ladder, the ladder not going to change, right? Ladder is 13 feet, all right? Okay, so now let's take a look. So the number 3 here, the step number 3. So for this problems here, this one is pretty easy here. So I'm be able to relate the x, y, and the constant. So what is the constant here is 13, right? So for this one here is a super easy one, is because the height, this is right, because this is the wall, right? So like, hey, I can see this is what the right triangles here. So then you can say what is the relation here? You can say this is x squared plus y squared is equal to 13 squared. So like I said, for this problem, this probably is very easy, but for some of the problem, we're going to take a look at some other problems, from the lecture notes. Some problem probably is not that intuitively, that probably are not that straightforward, all right? Okay, so this is step number 3 here. That's okay, now the remaining part, like I say, it will be pretty easy here. So the step number 4 is they will tell you, they say, hey, differentiate. So they say differentiate the equation. So whatever the equation, right? So differentiate the equation in the step number 3, you like one I highlight with respect to the time. Okay, then by implicit differentiation. So remember, all these variables, they are related to what? They are related to the times, right? So that's why when you take the derivatives, right? So you need to use the implicit differentiations, and then by chain rule, right? So you do the dt's part, okay? So now let's take a look at here. Let's see here, number 4, what that means here. They say, okay, take the derivative respect to t by implicit differentiation. So I know the x is a function of the t, right? So when you take the derivative, what is here? This is 2x, correct? But x is related to t, so by the chain rule, I need to have a dx what? dt, correct? Okay, now I have here, and then here, now I have this one here, this is dy, right? 2y, and then here this is dy dt. And what is here? This is a constant, so the constant, this is zeros here, okay? Then you say, oh, that is good, right? Because I'm looking for the dy dt. Okay, so now you say the dy dt, you move the 2x in here, so this will be what? The dy dt will be the negative y over x, all right? And what? dx dt, right? So you just move, so this is 2y dy dt is equal to the negative 2x dx dt, right? Then you just divide by, divided by 2y, you will get dy dt, and that is what we are looking for. Okay, so that is the step number 4 here. So that is a pretty easy step. Like I said, the hardest one probably is number 3. Okay, so now number 4, after you do that, number 5 here, you say, how do I do that? And so let's substitute, okay, all the known quantities, okay, in the result from step number 4, okay, and solve for the unknown. Okay, so now in here, in the number 4, okay, let's back to here, right? So we already said, okay, so this is what I want to find, is dy dt. Okay, so now in here, let's say they said number 5 said, go back to your problem and see all the unknown, substitute all the known here. So you say dy dt is equal to, okay, so there's one other constant I did not use here. Take a look here. So let's say when the bottom of the ladder is 5 feet from the wall. Okay, so the bottom of the ladder, that means from here to here is 5. Right, so that means my x here is 5. Okay, if x is here is 5, what is the y? Okay, so because this is the fixed, right? So the y, so I know the x squared plus y squared equal to the 13 squared. So y squared is related to x squared and the 13 squared. So right now when the x is 5, so this is a 5 squared plus y squared is 169, right? So the y squared is what? 25, so 144, right? So y is equal to what? Y equal to 12 here. Okay, so that is how do you get y equal to 12? And don't forget, you have negative signs here, right? So it's a negative sign. Then the dx dt, so where is this dx dt? Oh, here, we defined here, it's 2. Okay, so times 2. Okay, so you will get this one here is negative 5 over 6 feet per second here. So what's that mean? That means your ladder going to go down, at a rate 5 over 6 feet per second. That's what is this negative sign means, right? Because if you're going down, that means is, this is the the rate of the change. So if you go, so typical, we say you go right is positive, go left is negative, go up is positive, go down is negative, right? So that is what we said, okay, so I know my, I know my ladder going down at a rate of what, 5/6 feet per second here, okay? Okay, now let's take a look. Let's do one more practice here, okay? And then let's take a look. They said a sphere ball has its diameter increase at 2 centimeters per second. How fast is the volume change when the radius is, when the radius is 10? Okay, so let's follow the step here. Okay, so this is the step. Number one, they say, hey, do a picture. You say, okay, do a picture here. So this is a sphere. Okay, so of course I drew a kind of terrible, but it's okay. So you see here. Okay, so this is a sphere. So in here, from here to here, this is my radius. Now this is my diameters, right? So X is the diameters here, right? So this is the diameters here. That's what the picture looks like. Okay, so the step number 2, okay, so give all the unknown, okay? So in here, I only have one kind of variables here. So I will say X is equal to the diameter. Okay, and then V, because they want to find what the volume changes, right? And the V is equal to the volumes, right? Okay, so what is the other we are given? Oh, here, right, they say 2 centimeter per, the diameter is increased, is 2 centimeter per second. So that means the dx dt is 2 centimeter per second, right? Okay, so this is related to the information we try to find. And then they say, how fast is the volume changes, right? Okay, so this is the v dv dt. This is unknown. And this is that's what we are looking for, right? So let's try to highlight. So this is what we want to find, right? So that's the problem we try to solve. Then the step number 3, like I say, probably is the hardest step. So the step number 3 is here, okay? So this one is pretty easy, right? Because we find the equation. So V is equal to what? 4/3 pi r, right? We know in general is V is equal to the 1/3 pi r what? Cube, right? So this is the, this is the radius, right? So now for this province here, because X is the diameter, so what is here? The radius will just be what? X/2 to the what? Cube, correct? That's step number 3. Okay, so now let's take a look at step number 4 here. Okay, so the step number 4 say, hey, take the derivative of both sides. Okay, so I said dv dt is equal to 4/3 pi, so power rule, right? So power rule, so move this one down. So it's a times 3 and the x/2 and the 3 minus 1 is 2. Then don't forget what the chain rules, right? So this is the chain rules, right? You need to do inside, right? So don't forget that. Then you combine the simplified a little bit. So here, this 3 and this 3 cancel, this 4 and this 4 cancel. So I really only have 2 and the pi x squares, right? Okay, so now that's good. Okay, now let's step number 5 here. Let's see here. So we want to find the dv dt. right? So dv dt is equal to pi x squared over 2. Okay, now read here. They said when the radius is 10 centimeter, so this is the given constant, right? So when the radius is the 10 centimeter, so this is a 2 pi, right? So because the radius is 10 centimeters, so what is the x diameter is twice of the radius. So x will become what? It's 20, right, to the square. So now you simplify that. So this is the, and so this is the pi over x squared, pi over x squared of 2, and then the dv dt. Did I miss any constants here? When the radius is 10 centimeter, let's take a look. Okay, oh yeah, so here, that's my bad. Here, when we try to take the derivative here, I forgot to write it here, is dx dt. All right, be careful. This is what? This is the implicit differentiations, right? Because the x is a function of the t also. So that's why you need to do this is dx dt. That's my bad here. So the here, this is a dx. Don't forget you have a dx dt's here. Okay. Okay, so here, so this is the dx dt. Okay, so now the dx dt is what was given. So you times 2, right? So dx dt is here. So it's here, you times 2. That's why, I was not very careful to do that. So now this is what you have here. You have 400 pi centimeter cube over seconds here. That means if the radius, if the diameter increase in the 2 centimeter per second, then the volume of this sphere ball is going to increase 400 pi centimeter cube per second here. Okay, so that will be your final answer. So for this ones here, the first two are pretty basic. All right. So basically, like you use the relation, you are well off. And then remember, after the step number 3 is here, then you take the derivative of both sides. So like in here, don't forget like, what I did a while ago, I forgot to write this one down, right? So you need to make sure you have the implicit differentiation on both sides with respect to t. All right. And so let's take a break in here for our first videos here. So the second video for this lecture, let's take a look at a little bit more advanced type of the related rate problems here. Okay. All right. It's nice to talk to you, and I hope you have a good day. So, all right. Looking forward to talk to you to work more on the related rate problems here. Okay. Bye.